How about something a little more challenging? Take a look at this type of equation. It looks a bit intimidating at first, but we're going to try to recycle some of our techniques from our intermediate algebra course to see if we can apply it to this particular example. So a lot of times when I'm seeing a problem like this, I notice that I have exponents that are double the exponent on the e for the middle term. So e to the 2x minus 5e to the x. And I'm going to call your attention back to maybe a previous problem that you've done in another math class. And it's probably been a while, so let's just kind of review. When we solve equations like, I'll say, y squared minus 5y equals 36, I'll also like to look at the exponents on the y's. Notice that you have an exponent of 2. And I know you don't see it, but when I write it in, you'll see right away you have an exponent of 1 on this y. And again, there's that pattern. The exponent, one of the exponents is double the other. We know this type of equation as a quadratic equation. And with a quadratic equation, you know kind of the techniques of, oh yeah, we're going to move the 36 to the other side. I won't line it up because I know it's not a like term. But then we can solve I squared minus 5y minus 36, and we have our fun because we're pretty good because we practiced these types of equations before. Now, something a little bit more of a step up, sometimes you would see problems that have the same type of style. So if I can, another sidebar here. Let's suppose you saw, I'm just making this up, but I'm maybe using a different variable, u to the 6th minus 5u equals 36. And actually, I want to do it this way, 5u cubed. What we would do when we see this type of equation is, again, take a look at the exponents on the variable. I have a 6 and a 3. And again, there's a pattern of this exponent being double the other. We also see a constant on the right-hand side. So this type of equation is what we call kind of the technique of something that we would use a substitution for. So if I could, I'd pick a different variable. I don't want to get confused with the original variable of my problem. So I would say, a little substitution. I kind of go with this middle term, and I would say let's pick a number, or not a number, a letter, anything other than u, y, or x. I'm just any other number. Getting excited here. What would be a good one? I don't want to use, I can use the z, I suppose. Here we go, we'll do a z. Make sure it doesn't look like a 2 though. And I let it equal the variable, u to the 3rd power. So it's always kind of the way this goes. And if that is the case, you could kind of rewrite your equation in terms of z's now, substitution method. So if z is equal to u to the 3rd, consider this way. What happens if you saw z squared? So if you saw z to the power of 2, then that would be the same thing as u cubed to the power of 2, which is the same thing as u to the 6th. So you actually can replace both of your exponent expressions in terms of z. So if that is the case, u to the 6th is actually rewritten as a z squared minus 5u cubed is z equals 36. And look what we have turned our equation into. We have turned it into something a little more exciting for us because we have a technique on how we solve these quadratic equations. The issue, though, is that when you would solve this quadratic equation, when you solve it for z, we would have an issue because the original equation started with a u. So we would have to remember to resubstitute later. So don't forget that. Now, if you need to take a little time to review this technique, this is from an intermediate algebra course. It's called substitution. And so if you want to go through that, feel free to. And it's usually substitution when you deal with quadratics, not the substitution method when you are using systems of equations. I know, so many techniques. So feel free, play along, but I'll show you how it applies to our type of problem, a little bit more, more college algebra application. So again, having seen these previous examples or just being able to recall there was some sort of thing we did in the past, I'll notice again the pattern. I have variable in the terms of e in a sense. I have a double e to the 2x. That 2x exponent is a power, not a power, it's double the exponent on the e, which is just an x. And what happens is we can make this substitution. I always look at this, it's called the linear term in a sense, but I know it's not really linear. This e to the x, I'm going to substitute. And I'm going to I gotta pick something other than an x. So I'm gonna go with a y. So I'm gonna let y equals e to the x. Now, if that is the case, the same idea is happening. If you want to figure out what is e to the 2x, you can think backwards, sort of, if you want to play with me. If I say e to the 2x, right? Another way to talk about e to the 2x is to rewrite it as e to the x squared. Well, if that is the case, what's happening is that is really y squared in both cases. So really, if you just stick with, letting a different variable equal your, I guess, your term or your factor that has a smaller exponent, you could kind of convert this to the other exponent has to be in terms of squares. Remember, the goal is to get it to look like a quadratic equation. So what we do at this point, we would then resubstitute everything in a sense. So again, covering up that 2x, so you see this. Instead of e to the 2x, we would call this a y squared. We still have a minus sign, we still have a 5. Instead of e to the x, we would call this a y. And then we still have the equal sign, which is 36. And look what we have here is the quadratic equation. So excited, huh? We get to solve this now. So we have a kind of a better idea that when we have the quadratic equation, we now can say, oh, that's y squared minus 5y minus 36 equals 0. And then hopefully it's going to factor. If not, we have other techniques. But I am looking at factors of negative 36 that add up to negative 5. So I remember like 9 times 4. The negative should be on the 9. I'm extremely happy to have a 1 in front of the squared term because that makes the factorization a little bit nicer for us all. Y times y. And we can directly use our factors. So y minus 9 times y plus 4 still equals 0. And then you're automatically saying, oh yeah, I said each factor equal to 0. And then what happens? You add 9 to both sides, you get y equals 9 or y equals negative 4. Now, be careful. You have just solved the equation that's dealing with y. So you kind of have to be careful that, okay, we know that solution, but we don't want to find who y is, we want to find who x is. So this is where we go back to our substitution. And we want to say, don't forget, we're going to resubstitute. And this is where, I didn't spell that right, resubstitute. I try whenever I can. And I want to go back to, hey, y was equal to e to the x. That is a big deal. We forget that, then we have not solved our equation. And this is the college algebra portion now coming at you. If we do this, what's going to happen You have y equals 9. So that's saying e to the x equals 9. Or y equals negative 4. So instead of y, we would be saying e to the x equals negative 4. So my friends, we now have ourselves exponential equations that we have to solve. You're probably wondering, when was this going to come into play? So I'm going to take those off to the side. I need a little bit more room based on our previous thoughts. So let's pull this over here. I know there's a lot of writing coming on here, but I want to move this off so I have a little bit more room to think. So I have e to the x equals 9, or e to the x equals negative 4. So let's just solve this with what we know. A little bit of issue here is that we have an exponential equation, and I know we can never match e with anything in terms of bases. So this gives me a hint. Aha, we're going to have to take the natural log of both sides. So I'll do that with the e to the x and the 9. And what happens when you take the natural log of e to the x, you can either use your property or you can move that. There's two properties you can apply, but I'll move the x in front. I now have natural log of e equals natural log of 9. And then natural log of e, if you remember, I know sometimes you won't because we haven't dealt with it as much. Natural log of e ends up being a 1. So we do have x times 1 equals natural log of 9. But x times 1 is just x. So we have a solution, x equals natural log of 9. And if you were to try to type that into a calculator, you're going to get some sort of decimal approximation. So that's feeling pretty good. I'm noticing like, okay, natural log of 9, nice number, no error pops up if I use the TI. We're going to take the same approach on this e to the x equals negative 4. So if we were to do that, what do you have? Natural log of e to the x equals natural log of negative 4. And right away, what's causing issues for me, you can go through the whole technique again, but this should probably start alarming you. I'm saying, wait a second, this is a negative argument. We could never have this. So this particular case does not make sense. This is what we call, I should say, it leads to a no solution. It doesn't work. So we're going to negate this case or omit this case, ignore case. So that leaves us with the only solution to be natural log of 9. Now, I want to kind of even prove this even further. I know you probably are taking my word for it, and I totally appreciate that you trust me at this point. But you know, a lot of times it's always good to ask why. Why can I just ignore this case? So I'm going to pull up the TI for you and kind of show you. Let's just even look at this example e to the x. Let's just look at the graph just so that we can see. Let's switch screens for a second. I really want you to believe me. I question things sometimes, right? So let's take a look at what does e to the x look like if I were to graph that in my TI. E to the x. There we go. Press enter. A little slow to respond to me. There we go. Now let me graph based on my window. And you see what we have here is an exponential function. And if you remember properties of exponential functions, this is a parent graph. The x-axis acts like an asymptote, a horizontal asymptote that it never passes. So if we were to look at what's happening at the far end, the far left of this graph, you'll notice that no matter what you do, you can either do this by tracing. I don't know if you want to look at what's happening to the y values. As you get to smaller values of x's, the y values are still getting super, super, super small. You can keep playing. But you know when we see this little e to the negative 4, that's scientific notation for saying, hey, it's a number that's really close to 0. A lot of zeros in front. Let me see if I can I'll go backwards a little bit. The more zeros you have in front, then you'll start seeing this scientific notation business happening. Well, my friends, what this is trying to say is this exponential function, as long as it's in its parent graph form, it's not shifted, this exponential function is never going to be equal to a negative number. So when you go back and you look at your statement of this second case right here, I'll highlight it in purple, this is kind of a false statement because exponential, e to the x is never negative in this case. So that's why you could ignore it. If that doesn't, like if you don't see it ahead of time, no worries. Just check out when you go through all the steps, and we can even go back and prove this if you don't like looking at the graph and trying to understand it. You know what happens if you type in natural log of -4? Let's go back to our TI really quick. And this is kind of a strong, go back to the home window. Natural log of -4. Press it and check it out. It gives you something that's not real, like an error message. And that's another heads up of saying, hey, that case is not gonna work. So feel free to approach it either way, but you just gotta be a little careful when you're going through these. So that's a fun one. I do realize, and I like to show you just so that you have that experience behind you. Another similar example that's kind of in this section, I'm going to, while I have your captive attention, I'm gonna look at, looking at example 8. And you'll notice that when you play with this type of log equation, let's go with it, you'll see that the logs are on both sides. So at this moment, it's a type 2 log equation. And with this type 2 log equation, before we start and try to solve everything, we want to say, okay, well, how about if we try to condense them to single logs? So if you look at the left-hand side, you'll notice, oh yeah, they have the same base. The base is 2. So if that's the case, you can rewrite them as a single log with that base of 2. And if there's an addition sign in between, we get to rewrite it so that we are multiplying the arguments. And similarly, if you look at the right-hand side, you will notice that the base is 4. So you can rewrite them as a single log, but you have to remember the base is 4. And there again is an addition sign in between. So that would leave us with multiplying the 2 arguments. So in this case, it's 2 times 8. Now, feel free, if you wanted to simplify, you would have log base 2 of x squared plus 3x equals log base 4 of 16. Now, normally in type 2 equations, what we're supposed to look for is if you have everything condensed to a single log on the left-hand side, everything condensed to a single log on the right-hand side, what happens is you can kind of say, well, what if, are we able to set the arguments equal? Now, before you even do that, you want to double check one thing. Let's highlight this. Check it out. Notice that the bases are not the same. And in our past math classes and some of the previous examples, it would allow us to, we never saw this case, by the way. We would just say, well, okay, we're stuck a little bit. So before I give up, I want to take one last shot at this. And I notice, and this kind of really stands out to me after doing like millions of these, I'll notice that this logarithm has a numerical base, which is 4, and a numerical argument. And that numerical argument, let's spell argument right, argument, there we go, is 16. And whenever I have a base and an argument both being numbers, there might be a better way to write log base 4 of 16. Maybe there's a nicer number that I can get rid of the log. So just look for it and say, well, maybe I just need to figure out how to evaluate it. So if my TI has that capability, I can type that in. If I don't have a TI around, what I might do is say, hey, I don't know what that number is, but I can set it equal to a variable. For sake of confusion or non-confusion, I won't use X because that's our equation. So let's just use Y. If you guys remember, if you're evaluating this, you can convert it to exponential form. 4 to the Y equals 16. And then you can say, oh yeah, exponential equation, I can try to match the bases. Well, I know 4 and 16, those come up very common. 16 is 4 square. So what happens, bases match, set the exponents equal. Wait a second, this log base 4 of 16 is not just log base 4 of 16, it's another way to say 2. So this is another issue that could come along. So let me kind of go back to the equation and let's replace it. We're going to replace this with a 2. So no more log on both sides anymore. It's just a 2. Let's go back. Log base 2 of x squared plus 3x equals 2. Now what you've just done is this is now a type 1 equation. And with type 1 equation, you notice there's a log on one side and a constant on the other side. From this part, we can now change to exponential form. So remember exponential form, we take the base, which is 2. We're going to raise it to the other side. It happens to be a 2 as well. And we're going to set it equal to the argument, which is x squared plus 3x. If you want to simplify 2 squared, what do we get? 4 equals x squared plus 3x. And right away, you're like, ah, I love it when this happens. I've got myself a quadratic equation. Bet you're wondering, why do we spend so much time on chapter 3? Ah, now you know. So with the quadratic equation, I'll take that 4, I'll move it over, and hopefully I'll see something nice that I can factor. So I have 0 on the left side, x squared plus 3x minus 4. And so what I'm looking for, I'm going to factor this, is I'm looking for factors of -4 that add up to 3. So 4 times 1, I know that. To get a positive 3 and a -4, the negative should be on the 1. Again, I'm grateful. Super happy in this course. Most of the time we are getting coefficient of the squared term to be 1. So that factors nicely because the only way to make an x squared, x times x, and we can use our factors directly. And so you've guessed it. Oh yeah, set each factor equal to 0 now. And we get our solution. Let's see, x equals -4, x equals 1. And I feel pretty good about myself, but I have to warn you that this was not the original equation. You know, the quadratic equation is great. We got 2 solutions, but where did we start in the first place? Go back, go back, go back. It was a logarithmic equation. So when you look at your log equations, see if I can put this on the same screen. I'll just copy it over if possible. I'll do that. Okay, so log base 2 of x. I have a very short memory, so I'll shrink it and then write it so we can see it for ourselves. Okay, so we're gonna look at, that's gonna be really big. Log base 2 of x plus log base 2 of x plus 3 equals log base 4 of 2 plus log base 4 of 8. I just want you to refer to this in a second. Okay, so I'll open that up just a little bit more. Okay, now what I'm concerned about the 2 arguments. This right-hand side of the equation, we both had numerical arguments. We are good to go on this. No matter what the values of x are, these still are going to be the same values. So this is kind of where we end up with the idea. If you look at x equals -4, X equals -4 makes an argument. It makes actually both arguments negative. And if you're not sure, you can say, oh yeah, right away, this is where I have the issue. But you could also see it in the other argument too. So right away, we know that we cannot include this. We have to throw it out. Now check this again with x equals 1. If you have log base 2 of 1, we're good to go. It doesn't make anything negative. What about the next one? Log base 2 of 1 plus 3. Well, 1 plus 3 is 4. We're still good to go. It never makes the argument negative. So x equals 1 would be an appropriate solution. So then you can say, okay, finalize this, write this in the solution. If you want to make fancy braces, you should just have a positive 1 as your solution. So see all these things we kind of run into. I just want to kind of give you some experience. Remember, it's not always as straightforward as when you see the first example versus the last example. But don't be afraid to pull things out from your past that you haven't used. That's kind of the beauty of all this, is we're kind of trying to connect things to what we've already learned. So I just wanted to give you some experience. I really hope this helps. I'll see you in the next section.